Hi, my name is Vineet. I'm the co-founder of Succeed Easy Tutorials. In this video, I shall talk to you about scientific notation. Let's start with the introduction of scientific notation. Let me take the same example which I had taken in my previous video for sake of data. Let's take that. So suppose we measure a building's length as, let's say the building's length is 270 feet measured up to the nearest 10 feet. And if there is a tank over it which is 16 feet, but that is measured up to the nearest foot. Mind you, there is a difference, a stark difference between the two, right? So just focus on this. What will be the arithmetic total? The arithmetic total would be obviously 270 feet plus 16 feet, that is 286 feet. But if we represent it, the addition or the total length, if we represent it as 286, it will be wrong. We saw that in the previous video, right? Why it will be wrong. Here, the least accurate measure is up to the nearest 10 feet, right? That's the least accurate measurement, right? So we round it to 286 feet becomes 290 feet rounded to the nearest 10 feet, right? Because 6 is greater than 5, then we round it up to 290 feet. Got it? But the point here is, how do we represent this data with the right accuracy in a form in which there is no ambiguity? So that's where scientific notation comes to our rescue. So let's take this example now in detail. So the building height is 270 feet measured up to the nearest 10 feet, right? The actual measurement could have been 266 feet, or it could have been 267 feet or 268 feet, whatever, right? I mean, that would be the case of rounding up. So this will be all this data would round up to 270 feet. Or else the same data could have been, let's say, 270 feet, 272 feet, 274 feet. Anything less than 275 would round down to 270 feet, isn't it? So there is ambiguity involved in this data. What's the way out? The way out is scientific notation. How do we do that? So the building height is 270 feet measured up to the nearest 10 feet. We know that it is up to the nearest 10 feet, meaning the rounding is at the tens place, isn't it? Therefore, actually, it has only 2 significant digits and not 3. So how do we express this correctly using the scientific notation is with like this. We say 2.7 times 10 to the power 2 feet. Now look, there is a standard way in which we get this part, right? And then we take a multiple of 10, which I'll show to you in a while. Stay with me, please. Let's take another example. The total length, right? That was 290 feet. Again, that is ambiguous because the level of accuracy is only up to the nearest 10 feet. So we have to consider 2 significant digits here as well. And therefore, as before, 290 feet is correctly represented as 2.9 into 10 to the power 2. This shows that it has only 2 significant digits and not 3. This and the previous example were exactly the same, okay, except for the data part. Now look, what is standard notation? Standard notation is the normal or usual way of representing data. Okay, please note, this is not scientific notation, this is standard notation. Please pay attention to the word, okay, because you may get carried away and you may think that this is scientific notation. No, this is standard notation. Okay, so this is the usual or the normal way in which we write data as 14, 15.25, 600, 17.6, and so on and so forth, right? Now, what is scientific notation? Scientific notation helps us to conveniently express very large or very small numbers or quantities. It also helps us in expressing the correct level of accuracy, that is by way of significant figures, okay? And we saw that in the previous examples, the 2 examples that we took, okay? So here comes scientific notation. Mind you, it is scientific and not standard, okay? So scientific notation is also called scientific form or standard index form or standard form in the United Kingdom, okay? Scientific notation or standard form, it is expressed as a number m times 10 to the power another number n, such that the number m is expressed as 1 is less than equal to m and m is less than 10. That means m has to be between 1 and 10. M could be equal to or greater than 1, but m has to be less than 10. That means the value of m can never be equal to 10. It is m is always less than 10, but m can be either equal to 1 or m can be greater than 1. Do you get it? So the number, this number m is always between 1 and 10 such that it could be equal to 1 or greater than 1, but surely less than 10. Alright, please mind it. Okay, and n, this power n, it could be a positive or a negative integer. Okay, so this is the scientific notation or the standard form of expressing numbers. Let's do certain examples to understand how do we convert between standard notation and scientific notation or standard form. Okay, so as you can see on your screen very clearly, 3000 can be expressed as 3 times 10 to the power 3, right? These 3 zeros easily converted to this basically means 3 into 1000, and 1000 is basically 10 to the power 3. So we straight away get this 3000 as, we can write it as 3 into 10 to the power 3. Second number 240. Again, we need to take a number, we need to choose a number and then multiply by 10. So what we can do is, and mind you, we need to get a number m such that it qualifies this 1 is less than equal to m and less than equal to 10. So this number should not be written as 24 into 10. This should not be expressed in the scientific notation like this, because 24 in this case, m, that is your 24, will be greater than 10. We cannot do that. It has to be less than 10, right? A number less than 10. So what we do, we need 2.4. How do we get 2.4 from 24? By dividing it by 10, right? So here 4 divided by 10, right? And therefore we need to again multiply it by 10. And here we already have 10, right? So multiply it by 10 again. So what do we get here is essentially 2.4 into 10 into 10 is 100, that is 10 to the power 2. I hope this is very clear to you. Okay, same logic, 0.0007. So here in this case, we want a number m which is between 1 and 10, and the number m can be equal to 1, but it cannot be equal to 10, right? So the number here that we want is, how do we convert that? We want this, we want actually to segregate this number 7. So when we do that, how do we do? We take 0.0007. okay, so if you just remove this decimal, that means you are dividing this entire number by 1, and then how many zeros? 1 2 3 4, 1 2 3 4. That means 10 to the power 4 is in the bottom. Using the rules of indices, you know that a to the power m is equal to 1 upon a to the power minus m, right? Or vice versa. That is a to the power minus m is equal to 1 over a to the power n. So therefore here in this case it is here in this case the bottom is 10 to the power 4. It goes on the top and it becomes 10 to the power minus 4, and therefore 7 stays as it is. So 7 into 10 to the power minus 4, right? I hope this is also very clear to you. Now let's take very large number called Avogadro's number, which we often see this in scientific calculations, right? So the number is like this. It is 602,300, and then followed by how many zeros? There are 18 zeros. 3 3 6 3 9, and then again 3 12, 12 plus 3 15, 15 plus 3 18. So these are 18 plus 2. There are 20 zeros in all. Okay, so how do we, and this is the standard notation. Okay, how do we express this in the form of scientific notation? So we want to find this m, and we want to find our n such that 1 is less than equal to m, m is less than 10, and n belongs to the set of integers. That means n could be a positive or a negative integer. So first level is, take 6023. What we want to extract from here is, we want this number 6. I mean that number has to be, we want that number m that qualifies under this rule, right? So we cannot take 6023 as it is. We cannot take even 602 as it is, because m has to be less than 10. So what is that number which will be less than 10? Obviously that number is going to be 6 point whatever. Okay, 6 point whatever digits are follow 6. That means this number is between 6 and 7, which qualifies to be m, right? But how do we convert 6023? into 6.023. What do we do? So basically what to convert this is, you take 6023 and you divide it by, you want the decimal after 6, so there are how many digits ahead of 6? There are 3 digits. So what you do, divide it by 1000. When you do that, what you are going to end up with is 6.023, correct? Now that you have divided by 1000, that means you will have to multiply this number by 1000 so as not to change the value, isn't it? So 6.023, or rather 6023, can be expressed as, not 6.023, please consider 6023, the first 4 digits from this number, Avogadro's number. 6023 can be conveniently represented as 6.023 into 10 to the power 3. Up to here, are we clear? I hope yes. Okay. So how do we convert the entire number? Now look, count the number of zeros. We already counted that. How many zeros are there? We have handled only up to here, 6023. We wrote that as 6.023 into 10 to the power 3. Now we have to handle the rest. So how many zeros are there? 18 plus 2, 20. So that means straight away, if we take this number and multiply it by 10 to the power 20, then we should be cool, right? So the number is 6.023 into 10 to the power 3. We took this number as it is, multiplied that by 10 to the power 20, and this is coming from here, total 20 zeros. Okay, so what do we get? We get 6.023 into 10 to the power 23. Why? Because the rule of indices says a to the power m into a to the power n will be equal to a to the power m plus n, right? So therefore the indices, they get added when it's a case of multiplication, okay, the base being the same. So the final answer is 6.023 into 10 to the power 23. Then this is in scientific notation form. Now consider the significant digits, okay? See, as we know, the trailing zeros, they don't qualify to be significant digits until and unless there is a decimal sign at the last, isn't it? If there is a decimal sign, then I'll consider all the digits as significant. But as a matter of fact, it is not. The decimal is not there. So essentially, I have only 4 significant digits: the non-zero digits and the zeros in between the non-zero digits. So there are essentially only 4 significant digits, isn't it? How do we express this level of accuracy with the help of scientific notation? It can be seen over here. When we write this number in scientific notation, we write it like this: 6.023 into 10 to the power 23, and that clearly means that there are 4 significant digits. So the level of accuracy is correctly represented when we use scientific notation. Let's do one last example to wind this up. So if we consider 17,000, as already explained to you, there is no decimal there, right? So please, whenever you see the trailing zeros, please see whether there is a decimal at the end or there is not. Okay, so be conscious about it. So if you measured it correctly up to, now the point is, if you measured it correctly up to the hundreds digit, that means hundreds, I'm not saying hundredth, I'm saying hundreds. Okay, so unit tens hundreds, meaning up to this point. So if you measured this number correctly up to hundreds digit, then you can express the real accuracy using the scientific notation as below. So what you want to do is that, see, your level of accuracy was up to the hundreds digit. So what you can do is you can convert this number. See, normally if you will convert this number, you will not write this 0, right? Let's say if it is 17, then what will you do? You will just say 1.7 into 10 to the power 1, isn't it? That means you have not changed the value 17 as it is you have taken. If you take 17,000 and you convert it, then what you do? You will write 1.7 and you have divided this. You want 17. You want this number to be equal to 17,000, isn't it? So what you do? You multiply by 10 to the power 4, isn't it? So as to retain the value of 17,000, right? 1.7 times 10 to the power 4 will be 17 into 10 to the power 3, that means 17,000. So this is how you are going to represent. The point that I'm trying to communicate over here is that, look, here it is 1.7, but if you have measured it correct up to the hundreds digit, and you want to show that level of accuracy, okay, you are going to put another 0 here after 7. That means 1.70 into 10 to the power 4, which has 3 significant digits, as against 1.7, which has only 2 significant digits. Do you understand? Ignore this. Consider what we discussed later. Okay. So remember that if you want to show the right level of accuracy, then this is how you can correctly express the level of accuracy by using scientific notation, which clearly shows the level of accuracy that you want to depict. So with that, we come to the end of this video. You saw how we can easily and correctly represent the right level of accuracy using scientific notation. So if you like the content, please do subscribe, like, and share. I cannot wait to see you in the next video very soon. Thank you so much for watching. See you. Bye-bye.